Black holes are regions in space from which nothing can escape, not even light. And because nothing can escape a black hole, we can't see what's inside them. Black holes are mysterious. And since they're invisible, that mystery only deepens when we try to figure out how big they are. How do you measure something that you can't see? In this video, we explore one way astronomers measure black holes by looking at the edge of a black hole sphere of influence, known as its event horizon. Black holes come in a variety of sizes, but all have an event horizon. It is the boundary between the part of space-time where the black hole's gravity can be escaped, and the part where it cannot. The defining feature of a black hole. The event horizon of a black hole isn't really a physical thing. It's more like a boundary in space-time. It's the point of no return for anything that ventures too close to a black hole. Once something crosses the event horizon, it can never come back out, not even light. The size of a black hole's event horizon is called its Schwarzschild radius. It is the distance from the center of a black hole at which the escape velocity equals the speed of light. Escape velocity is the minimum speed an object needs to move in order to escape the gravitational pull of a planet or other massive object. For example, to escape Earth's gravity, an object needs to reach speeds of about 11.2 kilometers per second. But on the surface of a black hole, the escape velocity is infinite. So, anything that crosses the event horizon falls into the black hole. Black holes can be formed when giant stars collapse at the end of their lives. When a star runs out of fuel, it can no longer generate the outward pressure needed to support itself against the inward pull of gravity. Without this outward pressure, the star collapses under the force of its own gravity until it becomes a black hole. Black holes can also be formed when two neutron stars collide. Since black holes are invisible, astronomers can't directly measure their size. Instead, they infer the size of a black hole's event horizon by observing the behavior of matter near the black hole. One way to indirectly measure the size of a black hole is to observe the motion of stars near the black hole. Stars near a black hole move very fast as a result of the gravitational pull of the black hole. By measuring the speed of these stars, astronomers can calculate the mass of the black hole and then use that mass to infer the size of its event horizon. This method is often used to measure the sizes of supermassive black holes, which are the massive black holes found at the centers of most galaxies. Another way to indirectly measure the size of a black hole is to observe the light that passes through its event horizon. When light passes through a black hole's event horizon, it is bent and distorted by the intense gravity of the black hole. This distortion can be used to infer the size of the event horizon. This method is known as gravitational lensing. Gravitational lensing has been used to measure the size of the event horizon of a black hole in the center of the M87 galaxy. The size of the event horizon was found to be about 40 billion kilometers in diameter. That's about 3 times the diameter of our solar system. Accretion disks are another way to measure black holes. Some black holes have accretion disks around them. These are disks of glowing hot gas that forms as matter falls into the black hole. The size of an accretion disk can be used to infer the size of the black hole's event horizon. Accretion disks have been observed around many black holes, including those in the centers of galaxies such as M87 and NGC. The size of the accretion disk around M87's black hole was found to be about 30 billion kilometers in diameter. That's about 2 times the diameter of our solar system. A fourth way to measure black holes is to look at X-ray binaries. X-ray binaries are systems consisting of a black hole and a normal star that orbit each other. As matter from the normal star falls onto the black hole, it forms an accretion disk that emits X-ray. The size of the accretion disk in an X-ray binary can be used to infer the size of the black hole's event horizon. Astronomers have discovered thousands of X-ray binaries in our galaxy. But the size of the accretion disk in any one system can only be measured when the 2 objects in the system are relatively close to us. Quasars are fifth and final way to measure black holes. Quasars are extremely bright and distant active galactic nuclei. They are powered by supermassive black holes at the centers of galaxies. As matter falls into the black hole, it forms an accretion disk that emits huge amounts of energy, including visible light, X-rays, and radio waves. The brightness of a quasar is so great that it can outshine the combined light of hundreds or even thousands of galaxies. The size of a quasar can be used to infer the size of the black hole's event horizon. However, quasars are so far away that it is difficult to measure their size. One example of a quasar that has been used to measure the size of a black hole's event horizon is 3C2-173. 3C-273 is a quasar located about 240 million light-years away from Earth. The black hole at the center of the galaxy that hosts 3C273 is thought to have a mass of about 660 million times that of our Sun. The size of the accretion disk around the black hole was found to be about 400 million kilometers in diameter. That's about 30 times the diameter of our solar system. We know that there are plenty of black holes out there in space. We may never be able to see them directly, but we can observe their effects on other objects in space. In some cases, these observations can give us clues about the size of the black hole's event horizon by studying the properties of matter near black holes. Astronomers can learn more about these mysterious objects and the powerful forces that govern them, in addition to being fascinating in their own right. Studies of black holes have important implications for our understanding of the universe as a whole. For example, by studying the behavior of matter near black holes, astronomers can test theories of gravity and learn more about the nature of space. Black holes are also thought to play a key role in the evolution of galaxies. The supermassive black holes at the centers of galaxies are thought to regulate star formation and control the growth of the galaxy as a whole. By understanding how black holes interact with their host galaxies, astronomers can gain insights into the dynamics of galaxy formation and But despite all of these advances, there is still much that we don't know about black holes. One of the biggest mysteries surrounding black holes is what happens to the matter that falls into them. We know that matter cannot escape a black hole, but we don't know what happens to it after it crosses the event horizon. Some scientists believe that matter is destroyed at the event horizon, while others believe that it continues to fall towards a singularity at the center of the black hole. The singularity is a region of space-time where gravity is so strong that nothing can escape, not even light. We don't know what happens at the singularity because it is impossible to observe. Our current theories suggest that the singularity is a point of infinite density, but we don't know if this is true. Another big mystery surrounding black holes is how they form. We know that black holes can be formed when stars collapse at the end of their lives, but we don't know how common this process is. We also know that black holes can be formed when neutron stars collide, but we don't know how often this occurs. There is also evidence that some black holes may have been formed in the early universe, but we don't know much about these primordial black holes. Despite these mysteries, scientists are making progress in our understanding of black holes. New telescopes and other instruments are allowing us to make more precise measurements of black holes and their properties. In the future, we may be able to answer some of the outstanding questions about black holes and unlock the secrets of these fascinating objects. So, although we may never be able to see a black hole directly, we can continue to learn more about them by studying the effects they have on other objects in the universe. And by doing so, we can gain a deeper understanding of the fundamental laws that govern the universe. What do you find most fascinating about black holes? Let us know in the comments below. And don't forget to subscribe for more videos of Cosmos in a minute.